Okay, hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Nisa Irdina binti Nur Junaidi from Tuhelitu, and I'm going to talk about filter and its type of filters and the function and also the introduction of filters. Filter has 6 types of filters. First is low pass filters. Second is high pass filters. Third is band pass filters, band stop filters, differentiator and integrator. So the types that I've mentioned just now is various type of filters, and it has different functions and different use that will present by my other group mates. We will learn about the filters, which is the function. First of all, I'm going to talk about the function of this filter. The function, the usage is basically the filter is a circuit that is capable of passing or amplifying certain frequencies while attenuating other frequencies. It can pass other frequencies and can attenuating other frequencies too. So a filter can extract important frequencies from signals that also contain undesirable or irrelevant frequencies. That is basically the function of a filter. First, audio electronic. A crossover network is a network of filters used to channel low frequency audio to woofers, mid-range frequency to mid-range speaker, mid-range frequency to mid-range speaker, and high frequency sounds to tweeters. Analog to digital conversion is filters are placed in front of an AC and DC input to minimize aliasing, to minimize the paralleling, the tailing, aliasing, something like that, something tailing. In the field of electronics, there are many practical applications for filters. Examples include is first, radio communication. First is in radio communication. Filters also enable radio receivers to only see the desired signal. It means the signal that they have choose to show, then we use filter to select the desirable things only, the desirable frequencies only, the desirable signal, while rejecting all other signals, assuming that the other signals have different frequency content. So in this radio communication, the filters is basically to select, to choose the desired signals only, and the signals they didn't choose can assume that other signals have different frequencies and frequency content. Then the next example is in DC power supplies. Filters are used to eliminate undesired high frequency. Okay, in DC power supply, when there is high frequency, there is a high frequency that is abnormal, unusual than it used to be. The unusual frequency, the higher frequency will be terminated, will be removed, will be eliminated using the filters. For example, the excessive noise, the noise that is excessive. So This filter will eliminate the noise. Additionally, filters are used on a power supply's output to reduce ripple. The next example we can find this filter is at audio electronics. Audio electronic is a crossover network. It's a network of filters used to channel low frequency audio to woofers, mid-range frequency to mid-range speakers, and high frequency sounds to tweeters. The introduction of filters in RLC series circuit. As the frequency increase up to resonance, the current increase due to decrease in impedance. Impedance is symbolized as that. When frequency increase up to resonance, the current increase and the impedance decrease. When the frequency increase and the current increase, the impedance will decrease. Then XL is equal to XC. Then XL is equal to 2 pi FL, and is equal to XC is equal to 1 over 2 pi FC. Okay, the picture shown is basically the RLC series circuit. You can see the XL, the XC, the Z, and the frequency. Z minimum, I maximum. Okay, then after resonance, a further increase in frequency will result in a decrease in current due to impedance decrease. This is opposite to the recent one. Okay, when decrease in frequency will result in decrease in current, and due to impact of that due to the increase of impedance. Okay, when the frequency increase, the current will decrease and the impedance will increase. Therefore, a band of frequencies in which the current was relatively high, and outside this range, the current was relatively low. Outside it, the current is relatively high, is very high, and on the outside, the current is relatively low. It means it is lower than the inside. Okay, the picture shown is basically the after Renaissance, the RLC series circuit after the Renaissance. You can see the frequency there, and also when the Z is minimum, the I is minimum, and also the XL, the R, and the XC. Okay, a component which is designed, this is the filter. The filter is a component which is designed to block certain frequencies and pass others. Okay, filters is designed to block frequencies, and also it's designed to block certain frequencies and to pass certain other frequencies. It is to block and also to pass. This is the function of filter. The simple way to explain the function of filter, it is to first, it can block other frequencies, and it also can pass some frequencies. Okay, when the filter is above resonance, XL is higher than XC, and when the filter is below resonance, the XC is higher than XL. There are types of resonance, which is above resonance and below resonance. Above resonance, the XL is higher than XC, and the below resonance, the XC is higher than XL. You can see the picture shown is the graph of XC and XL, the reactance against frequency below and above the resonance frequency. Okay, you can see the below resonance, XC is obviously higher than XL, and the above resonant XL is obviously higher than XC. Okay, so that's all from me, and I'm going to pass this to my next group mate to present more about low pass filters and many more. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azim bin Mahdi. I'm from group at subject student from Tuheli 1. So my group got a project presentation about filter. So my subtopic is low pass filter. Okay, we start from what the meaning of low pass filter. A low pass filter is a filter that passes signals with a frequency lower than a selected cut-off frequency and attenuates signal with frequencies higher than the cut-off frequency. The exact frequency response of the filter depends on the filter design. The filter is sometimes called a high cut filter or treble cut filter in audio applications. A low pass filter is the complement of a high pass filter. In other words, low frequency signals go through much easier and with less resistance, and high frequency signals have a much harder getting through because they call low pass filter. They just through a low signal frequency and stop the high frequency signals. So a low pass filter have many examples, but I just take from acoustics, optics, and electronic. For acoustic, a stiff physical barrier tends to reflect higher sound frequencies and so acts as an acoustic low pass filter for transmitting sound. Like when music is playing in another room, the low notes are easily heard while the high notes are attenuated. Okay, for the optics example, an optical filter with the same function can correctly be called a low pass filter, but conventionally is called a long pass filter, which means low frequency is long wavelength to avoid confusion. The example of electronic low pass filters are used on inputs to subwoofers and other types of loudspeakers to block high pitch that they cannot efficiently reproduce. Radio transmitters use low pass filters to block harmonic emissions that might interfere with other communications. The tone knob on many electric guitars is a low pass filter used to reduce the amount of treble in the sound. Okay, next one. This is what I talked about the meaning of low pass filter. Okay, it only allows low frequency signals from 0 Hz to its cut-off frequency. FC point to pass while blocking those any higher. In low pass filter, it will pass low frequency signals, pass band, and attenuate or block at high frequency signals, which is stop band. Okay, this example diagram, like they say, like the meaning of low pass filter. They said signals from 0 Hz to its cut off frequency. So this is cut off frequency, which is they cut the frequency, the high frequency from getting through, and this is the low pass frequency. Okay, next page. Okay, low pass filter have two filter. The first one is we can call low pass RC filter. Okay, This is low pass RC filter. A low pass RC filter again is a filter circuit composed of a resistor and capacitor which passes through low frequency signals while blocking high frequency signals. This is okay. To create a low pass RC filter, the resistor is placed in series to the input signal and the capacitor is placed in parallel to the input signal such as shown in the circuit below. This capacitor and resistor. So with the setup, the below circuit, this circuit is a low pass filter. So you know this is a low pass filter. As a capacitor, is a reactive device. It offers differing resistance to signals different frequencies entering through it. A capacitor is a reactive device which offers very high resistance to low frequency or DC signals, and it offers low resistance to high frequency signals. As it offers very high resistance to DC signals, in this circuit, it will block DC from entering and pass them off to an alternative path. Alternative path, which means this, go to the right. On the circuit which is shown to the right by arrow, high frequency signals will go through capacitor since the capacitor offers them a very low resistance path. So high frequency will go through capacitor because the capacitor have a low resistance and go to the ground. Okay, remember that current always takes the path of least resistance, while low frequency signal will take alternative path. This alternative path, a lower resistance. Okay, next. Okay, this is the second type of low pass filter. Low pass RL filter. A low pass RL filter again is a filter circuit composed of a resistor and inductor which passes through low frequency signals while blocking high frequency signals. To create a low pass RL filter, the inductor is placed in series with the input signal and the resistor is placed in parallel to the input signal, such as shown in the circuit below. This circuit. How it works based on the principle of inductive reactance. Okay, inductive reactance is how the impedance or resistance of the inductor change based on the frequency of the signal passing through the inductor. Unlike a resistor, which is a non-reactive device, an inductor offers differing impedance values to signals of differing frequency, just as capacitor do. However, unlike capacitors, inductors offers very high resistance to high frequency signals and offers low resistance to low frequency signals. So it's the opposite of a capacitor. So they are not same. So based on this above, RL circuit works effectively as a low pass filter. It blocks high frequency signals from entering and allows low frequency and allows low frequency signals to pass through unimpeded. So the example of diagram, just same like a RC filter. The low frequency signal just take alternative path, and high frequency signals got blocked from this. Yeah. So the difference of RL filter, low pass RL filter and RC filter is to if you want to create a low pass RC filter, they need resistor is placed in series and capacitor is placed in parallel to the input signal. And for the RL filter, they to create, they need inductor is placed in series with the input signal, and the resistor is placed in parallel to the input signal. That's the difference of RL filter and RC filter. Okay, go to the next page. Okay, this is what I told you before. When at low frequency, they just go through to the alternative path. Yeah, like example, when at high frequencies, they go to capacitor. Okay, and the last one, this is the formula of low pass filter.
Assalamualaikum and good afternoon. My name is Muhammad Amin bin Razak and from 2Heady. Today I talk about for the subject electronic fundamental 2 for the topic high pass filter. First, for the meaning, high pass filter is an electronic filter that passes just with a frequency higher than a certain cut-off frequency and attenuates signal with a frequency lower than the cut-off frequency. The amount of attenuation for each frequency depends on the filter design. A high-pass filter is usually modeled as a linear time-invariant system. It is sometimes called a low-cut filter or best-cut filter. The high-pass filter has many uses, such as blocking DC from the circuit's tree sensitive to non-zero average voltage or radio frequency device. They can also be used in a conjunction with the low pass filter to produce a band pass filter. For the example, for the graph, you can see the graph goes upward. For the low pass filter, it is go downward. It is different with the low pass. In the optical domain, high pass and low pass have the opposite meanings. With the high pass filter, more commonly long pass, and passing only longer wavelength and lower frequency and vice versa. For low pass, more commonly short pass to block any unwanted low frequency components of a complex signal while passing the higher frequency. This is where we call we can see from the high pass to the from the upward to the downward. This is and in this, the stop band and the pass band, this is the cut-off region. Next, in high pass filter, all frequencies lying below the cut-off frequency are attachment FCR attenuated. At this cut-off frequency point, we get negative 3 dB, where this is negative 3 dB, and at this point, reactance of the capacitor and the resistor values will be same for the SC, and gain is calculated as, for the formula, gain decibel equals to 20 log over V out over V. And the slope of high pass filter curve is positive 20 decibel decades. After passing cut-off frequency level, the output response of the circuit increased from 0 to the VIN at the rate 20 decibel. From 0 to the 20 decibel, this is 6 decibel increase per octave. The region from the initial point to cut-off frequency point is known as stop band, as no frequencies are allowed to pass. The region from above the cut-off frequency point -3 dB point is known as pass band. This is known as pass band. At cut-off frequency point, output voltage amplitude will be 70.7% for the input voltage, 70.7%. Here, bandwidth of the filter denotes the value of frequency from which signals are allowed to pass. For example, if the bandwidth of the high-pass filter is given as 50 kHz, it means that only frequencies from 50 kHz to infinity are allowed to pass. At low frequency, this is the formula for the low frequency. At C is 1/2 pi phi f over C for the impedance is when the impedance is high for the T type, and for pi type is XL equals to 2 pi FL when the impedance is low and act as a short circuit. At high frequency, XC equals to 1/2 pi phi f over C when the impedance is low for the T type, and the SL 2 pi FL when the impedance is high and act as an open circuit. This is for the pi type and the T type. Just for the difference is at low frequency, the impedance is high when for the T type, and the impedance is low, and at low high frequency impedance is low for the T type and impedance is high. And the formula is for design impedance RO equals to square root L over C, and FC 1/4 is square root L over C, and L RO over 4 FC, and C 1/4 RO FC. And the F is the frequency of the input signal in Hertz, and FC is the cut-off frequency. This is the example for that we can see for the headphone or earphone. Using a stereo system as a practical example, a capacitor connected in series with a tweeter treble speaker will serve as high-pass filter, imposing a high impedance to low frequency band signals, thereby preventing that power from being wasted on a speaker inefficient for reproducing such sounds. In like fashion, an inductor connected in series with a woofer speaker will serve as a low-pass filter for the low frequencies that particular speaker is designed to produce. For the woofer bass, this is the woofer, and it is the low-pass filter for the low frequency. And the example circuit, the mid-range speaker is subjected to the full spectrum of the frequency from the stereo output. More elaborate filter networks are sometimes used, but this should give the general idea. When tweeter is the high pass and the woofer is the low pass from the stereo. High pass filter routes high frequencies to tweeter, while low pass filter routes lows to the woofer. And last, for the review, a high pass filter allows for easy passage of high frequency signals from source to load, and difficult passage of low frequency signals. And capacitive high pass filter insert a capacitor in series with the load. Inductive high pass filter insert a resistor in series and an inductor in parallel with the load. The former filter design tries to block the unwanted frequency signal, while the later tries to short it up. Where the former filter designed to block where the we can see the cut-off frequency on the signal, while the later tries to short it up. And the cut-off frequency for a high-pass filter is that frequency at which the output voltage is equal to 70.7% of the output voltage. And above the cut-off frequency, the output voltage is greater than 70.7% of the input, and the vice versa. That we can see that high-pass filter is different with the low-pass filter. And next, we can see another example for the filter. Thank you for watching.
Hi, my name is Bernard. I'm from 281. I'm going to present about bandpass filter. The topic has given to me, present. So, the introduction. Okay, bandpass filter is a type of passive RC filter that passes a selected range of band or frequency by connecting a casing together a single low-pass filter circuit with a high-pass filter circuit with often a band-pass filter. So basically, band-pass filter is a type of filter that passes low-pass filter and high-pass filter. So signal input enters to low-pass filter, then passes to high-pass filter, signal output, as you can see here. So the low-pass filter will block frequencies that are too high, and then high-pass filter will block the frequencies that are too low. Then will come out signal output. So this is the circuit diagram of the band-pass filter. So band-pass filter passes signal within a certain band or breadth of frequencies without destroying the input signal or introducing extra noise. This band of frequencies can be any width and commonly known as the filter band width. The cutoff frequency of the low pass filter must be higher than the cutoff frequency of high pass filter. So these are the diagram, the graph for the output and the frequency gain. And then the upper and lower cut of frequency point of a band pass filter can be found using the same formula as for both the low and high pass filter. For example, these are the formula for the frequency. So example, the value of the capacitor C1 required to give a cutoff frequency FL of 1 frequency with a resistor value of 10 is calculated the example below. So the upper and lower cut of frequency point of a band pass filter can be found using the same formula as for both and low and high pass filter. These are the example of the formula. And then uses. The band pass filter is most commonly in implementation of discrete proportional transform to separate out harmony. About 20% of filters used in computer music are bandpass. In audio amplifier application of circuit, such as in loudspeaker crossover filter or pre-amplifier tone control. So these are my present about bandpass filter. Thank you.
Okay, hi, assalamualaikum. Good morning. Okay. Today, I want to tell you or more about explain to you about topic 4 what I learned from Sir Hisham. Okay, first topic 4 filters. Okay, what I want to discuss specifically is band stop filter. Okay, as we can see here, band stop filter. Okay, I'm going to explain. Okay, first what we need to know is what is it. What is it is band stop filter. Okay, I got 3 points here. First, in signal processing, a band stop filter, or we can call it band rejection filter, is a filter that passes most frequency unaltered. Unaltered is mean tidak berubah, but attenuate is mean it melemahkan, something like that. It lemahkan. Those in specific range to very low levels. It is the opposite of a band pass filter. Band pass filter, band stop filter. Okay, 2. Band pass filter. Okay, band stop filter is opposite. It work opposite of band pass filter. Okay, A notch filter is a band stop filter with a narrow stop band. Okay, okay. Second point, narrow notch filter optical are used in Raman spectroscopy, live sound reproduction, public address system or PA system, and in instrument amplifier, especially amplifier or preamplifier for acoustic instruments such as acoustic guitar, mandolin, bass instrument amplifier, to reduce or prevent audio feedback while having little noticeable effect on the rest of the frequency spectrum, electronic or software filter. Other names include band limit filter, T-notch filter, band elimination filter, and band reject filter. Okay, third point here is band stop filter can be made by placing low pass filter in parallel with a high pass filter. Okay, you got it? Okay, next. Characteristic of band stop filter. Okay, first stop. What characteristic of band stop filter is stop transmission of frequency from low pass frequency and high pass frequency. There are two portions that I will explain later. Okay, as you can see, pass band, stop band, and pass band. Okay, stop band, you can see it go here. You will see it go here. It is stop or we can call reject the frequency. Okay, so the comparison in table, there are three types. Keep in mind there are three types: low frequency, resonant frequency, and high frequency. Okay, as you can see, I made a table. It can be in two: series element and parallel element. Okay, first we go low frequency. Low frequency Z maximum in series element, but Z minimum in parallel element. Okay, low frequency Z maximum series, parallel Z minimum. Okay, for resonant frequency in series element, minimum Z minimum, parallel element Z maximum. Okay, in high frequency Z maximum in series, in parallel element is Z minimum. Okay, you just keep in mind there will be opposite. Okay, if series element maximum, in parallel it will be opposite, minimum. Okay, so to simplify your untuk ingat, just you get it in mind in series element. Okay, so you will know it will be opposite in parallel element. Okay, next we go second. Okay, we go low frequency first. Okay, as you can see in series element, Z maximum, parallel element Z minimum. Okay, the arrow go through here is Z minimum, which is parallel. Okay, here Z maximum is series element. Okay, that is low frequency. Okay, second, resonant frequency. Okay, resonant frequency series element Z minimum. Okay, in parallel element Z maximum. Okay, it's simple to you memorize it. Okay, it will be opposite. Okay, as you can see here, Z maximum, Z maximum, Z minimum. Okay, series element Z minimum, parallel element Z maximum. Okay, you can see the arrow go through here. Okay, this resonant frequency. This is resonant frequency. Next, high frequency. The last one, high frequency, series element Z minimum, Z maximum. Okay, in parallel, it will be minimum. It will be opposite. Okay, as you can see at the picture, Z minimum, Z minimum, Z maximum. I think it's a bit little same with low frequency. Okay, here Z minimum, in parallel element, Z maximum is series element. Okay, that's the high frequency. So that's three type of band stop. Okay, first low frequency, resonant frequency, and high frequency. Okay, what you got here, application that used in daily, or we use we use a band stop. Okay, there are many types around the world, we know. Okay, so I got do some research, and I found this, and I met in a pointer. Okay, as you can see, first communication transceivers, second radio, marker beacon, ILS receiver, engine vibration monitoring system, automatic flight control system, flight director system, voice recorders. These are used to reduce the static on radio, which are commonly used in our daily life. Next, in image and signal processing, these filters are highly preferred to reject noise. These are also used in medical field application. In example, biomedical instrument like EGC, removing line noise. As you can see here, example that I got from my research: bandstop filter, low insertion loss, high performance, low VSWR, customized specs available. This type. This what I want to tell you specifically. As we can see, before I tell you that bandstop filter, it will give what we call it. We will, in bandstop filter, we have two portion. Two portion here. First, LPF, low pass frequency, and here we go through and eliminate. So in this portion, no response. It is high pass frequency. There are two. So there are two, and bandstop filter is what I said just now. This way, adding. So by adding low pass frequency and high pass frequency, we can existing bandstop filter here. You got it. Keep in your mind, there are three bandstop filter. First, we go from first. This this is conclusion. First, you bear in your mind there is bandstop filter, or we can call it reject filter or elimination or what else. Okay, so that is how it works opposite with band pass filter. Okay, it eliminate the frequency. Okay, just what I told you. Okay, second one, there are three type: low frequency, resonant frequency, and high frequency. Okay, there are three type. There are application in medical, in radio, what we use bandstop in our daily life here. Okay, please I think that's all from me, and I want to apologize if I mistaken. I done my research, but if I wrong, please tell me. Okay, so thank you all. Okay, please I hope this video will explain to you, will give you knowledge, will add some knowledge to you. Okay, assalamualaikum and thank you.
Hi, assalamualaikum guys. So I'm gonna explain about differentiator. Basically, differentiator consists of a resistor and a capacitor, could be used as a high pass filter. With square wave input and a short time constant compared to the input pass, it can be used as a differentiating circuit. So this is the example of input and output graph differentiator. Input pass V. So the time that the pass width is positive must be equal to the time that the pass width is negative or 0. This is a 0 or pass width negative, and this is pass width positive. This graph is voltage across C and R. The voltage output across C is a very close approximation to the shape of the input pulse. The shorter the time constant, the better the approximation. These two examples of calculation about to get time constant. So the example is C is equal to 10 microfarad and R is equal to 10 kilo ohm. Time constant equal to CR. So 0.000010 farad times 10,000 ohm and is equal to 0.1 second. So the output across R consists of two very narrow paths of opposite sign, one coinciding with the start, the other with the end of the path. So this is the example of formula. VR is equal to VO.
Integrator is an element whose output signal is the time integral of its input signal. It basically accumulates the input quantity over a defined period of time to produce a representative output. The two main types of integrators, mechanical integrators and electrical or electronic integrators. Mechanical integrators are the oldest application and are still used in metering of water flow or electric power. They were also used in control systems such as regulating flows or temperature. Electronic integrators, they're a form of first order low pass filter. They can be performed in analog or digital domain. It will have a low pass filtering effect, but when given an offset, it will accumulate a value, building it until it reaches a limit of the system or overflows. Voltage integrator is a type of electronic integrator, basically an electronic device performing a time integration for an electric voltage, thus measuring the total volt-second product. Current integrator, on the other, current integrator is very similar to voltage integrator. It also performs time integration, but for current integrator is for the current. It measures total electric charge. An example is the charge amplifier. In this diagram, the position of C, capacitance, and resistor R are changed and make the time constant large compared to the input pulse. So this could be used as a low-pass filter. In this graph, the input pulse to a RC circuit with a long time constant is shown, and the resulting output across the capacitor on the other hand. Basically, the integrator takes the input and produces an output across the capacitor over a period of time, so the output is directly proportional to the time integral of the input. Now there's some drawbacks to the ideal integrator. The bandwidth is very small and used for only a small range of input frequencies, and then for DC input, if frequency is 0, the reactance of the capacitance is infinite. Because of this, op-amp goes into open loop configuration. In open loop configuration, the gain is infinite, and hence the small input offsets voltage are also amplified and appear at output as error. This is sometimes called false triggering and has to be avoided. Applications of integrators. Op-amp integrating amplifiers are used to perform calculus operations in analog computers. Integrating circuits, they're very commonly used in analog to digital converters, ramp generators, also in wave shaping applications. Another application would be to integrate signal representing water flow, producing signal representing the total quantity of water that has passed by the flow meter. There's a video explaining more on the integrators.
The electron line. In this video, we're going to look at the integrator circuit. We can actually build a circuit using an operational amplifier such that the output voltage is equal to the integral of the input voltage. It's kind of interesting. So here we have our original circuit using the operational amplifier, where we have a feedback resistor and an input resistor, and we know that in this case the output voltage will be equal to the negative of the ratio of the feedback resistor to the input resistor times the input voltage. But what happens when we replace the feedback resistor with a capacitor? Remember that in an ideal operational amplifier, that the current going into the amplifier here on the input signal can be considered 0, and that the voltage from here to there can be considered 0 as well, because there's no voltage drop across here, at least not in an ideal operational amplifier. So when we replace that resistor with a capacitor, what do we get? Well, to find out how to relate the output voltage to the input voltage, we're going to keep track of the currents. First of all, we have a current from the input voltage to the input signal, and then we have a current from the input signal to the output voltage. And since there's no current flowing in this path, these two currents must be equal to one another. In other words, we can say that I1 is equal to I2. And using Ohm's law, realizing that this must be at 0 voltage, and there's the input voltage, we can say that I1 must therefore equal to the ratio of the voltage divided by the resistance. And on the second current right here, from there to there, notice that we are assuming that this is a positive voltage. This is at 0, so in essence the current will flow in the opposite direction, which means that we can write I2 as being equal to minus the capacitance times the rate of change of the output voltage with respect to time. We can now set those two equal to each other, see what we get. Here we get V sub I divided by the resistance is equal to negative capacitance times dV out over dt. So what we need to do now is solve that equation for the output voltage in terms of the input voltage. All right, we can do that by bringing this down here and this up here. So we can write V sub I times dt divided by minus RC is equal to dV output. Turning the equation around, we can write this as dV on the output voltage is equal to minus 1 over RC times V sub I dt. And now we can integrate both sides of the equation. We'll integrate this and we'll integrate it from V output at time equals 0 to V output at time equals t. And we're going to integrate this from, let's say, from 0 to t. Well, on the left side, what we're going to get here is we're going to get voltage output at t minus the output voltage at time equals 0, which is equal to minus 1 over RC times the integral from 0 to t of the input voltage times dt. Now let's assume that the output voltage at time equals 0 is equal to 0. We're going to set that equal to 0. So set V output at time equals 0 equals 0. So this disappears. And essentially we can then write that the output voltage as a function of time is going to be equal to minus 1 over RC times the integral from 0 to t of the input voltage times dt. And that is the solution we were looking for. What this is telling us is that the output voltage is equal to the integral, or proportional, not equal to because we have the minus 1 over RC there, but that it's proportional to the integral of the input voltage. Wow. So this is what we call the integrator circuit. What about R times C? What is that equal to? Well, it turns out that R times C is simply equal to what we know as the time constant, which tells us how fast the capacitor will be charging. If R is a large number, then of course it will take a long time for the capacitor to charge because the current will be smaller. If capacitor is a large capacitor, then of course it will take a longer time for it to charge because it has more capacitance. But if you then ignore that for a moment and you simply realize that then the output voltage is simply proportional to the integral of the input voltage, you then realize that this circuit right here is therefore called the integrator circuit because the output voltage is really the proportional to the integral of the input voltage. And that's how it's done.
So with that video, I'm going
Welcome
to
to
end the
Lecture Online.
presentation. I hope, thank you for listening.